Hi, I'm Xuetian. I will talk about our paper, Fast Neural Sync Flow. This work was done with Zhenqiao, Johnny, Francesco, and Simon. Some of the work was done during my research internship at Argo AI. This project is based on our NeurOps 2021 paper, Neural Sync Flow Prior. For more details, please refer to the YouTube link for the spotlight presentation. I will do a brief introduction to the neural sync flow. Sync flow F is the collection of all the translational vectors from point cloud S1 in time t-1 to point cloud S2 in time t. Traditional runtime optimization-based methods minimizes the point distance d between the two point cloud S1 and S2 to get the explicit sync flow F. Usually, an explicit regularizer C is added to smooth the estimated flow. For example, a graph Laplacian. However, it is a parameter-specific and discrete representation, and it requires heavy computation to construct the graph. Instead, Neural Sync Flow Prior proposed to use the architecture of a coordinate MLP as a new type of implicit regularizer. In this formulation, the explicit sync flow F is replaced by an implicit coordinate network G parameterized by theta. Therefore, the optimization becomes minimizing the point distance d to find the optimal network parameters theta. The neural prior in our method acts as a strong implicit regularizer that constrains highly dynamic motion fields to be as smooth as possible. Although Neural Sync Flow Prior has achieved superior performance in both dense large-scale point clouds or sparse point clouds, the computation time is extremely lagged that prohibits possible real-time applications. In the Neural Sync Flow Prior, we use Chamfer distance as a loss function, which exhaustively finds the correspondence between the source and the target point clouds, resulting in heavy computation during runtime. In contrast, we propose to use distance transform as an approximation to the Chamfer distance laws. Here we use a 2D example to show how the distance transform works. First, we construct the DT map using the target points by initializing the DT map to all zeros. Then, the rasterized 2D point image is set to 0 if a target point is presented in the grid, and set to 1 if the grid contains no target points. Finally, the DT map for the target point set will be constructed. After pre-compute the DT map, we could fix this DT map G in the entire optimization. Specifically, a distance between the deformed source point and the target point is queried by lookup in the pre-computed target DT map. Since the pre-computation of the DT map only happens once, and the distance query is just a table lookup, this distance computation is extremely fast during optimization. Now we take a look back to this table we had before. By applying the distance transform laws, our fast neural sync flow method gets similarly good performance to the NSFP, while being orders of magnitude faster. When testing a less number of points, our method achieves similar computation efficiency as a learning-based method, enabling possible real-time applications. Here is a breakdown of the performance. When testing a large-scale dense point cloud in Waymo Open dataset, our method achieves comparable performance while being 30 times faster. When tested on less number of points, our method achieves similar computation time as learning-based methods such as R3DSF and float. Here are some visual results we show on Argoverse and Waymo Open datasets. We also show 2D bird's-eye view flow for better illustration. Some applications, like depth densification and point cloud accumulation, are shown on the right. Please visit us in person at ICCV Thursday AM poster session 37. Please scan the QR code for project details.